Okay. All right. So, what I'm going to be talking about is how what natural language is I think, a cognitive computation rather than a, say, purely linguistic one, which is probably why it's relevant to you guys. Um, and everybody, I think, would agree that it has to do with symbols. Although I find in linguistics, you could find somebody who will argue about anything. And as to whether we have internal representations, for example, at all. And then what I'm going to point out is that these symbols have been data compressed, and that's why language looks as complicated as it does. And frankly, if it weren't for that, probably everything I'm going to say could have been discovered by Aristotle. And it's just that I think nobody noticed these things. And then a implication of this would be, we'll get to the end, that it allows computers, I think, to do cognition. And I'm a little worried that AI is going to stumble across this accidentally. So first, I'd like to do two warm-up exercises, very brief. One, I'm going to say a sentence and ask yourself, are you having any trouble at all with this? So he saw the saw that I saw. Anybody have trouble with it? I think it slid right down, right? So that's actually a little bit remarkable. Now, the second warm-up question, we're going to take warm-up exercise. We're going to take 10 seconds, and I want you to think, what are the parts of a chair? Okay. Now, did anybody have in their list glue, nuts, bolts, or screws? Okay. This will become relevant later, but wanted you to do it before you get biased towards thinking about things like that. So this is all part of what I think of as the Descartes-Cahal problem. You're starting out here, somehow you end up with this. And I'm not going to talk about how Shakespeare could possibly do this. I'm going to talk about how he could tell you these words and you understand what he's thinking. But in the course of that, we're going to be getting back to how does Shakespeare do this in the first place? So as far as understanding language, I think it's a much more amazing algorithm, whatever it is we do, than people really appreciate. And so I want to start off a little bit slowly and point out a few things. One is, I think it's a computation executed by neurons. Most of us biologists would agree on that. And what you're doing is one person has this three-dimensional, instantaneous, simultaneous picture in his head about something about the way the world's going around. Okay. But we're going to transfer that 3D picture to somebody else using a linear string of symbols that are ambiguous, because words usually all have multiple meanings. And they're arbitrary symbols, like the word cat has C-A-T, has no relation to a cat with two ears and a tail whatsoever. And the only relationship between these symbols is adjacency and succession. And somehow that doesn't trigger a bundle of associations in the listener's brain. It assembles a coherent picture of the world, the one that the speaker had. So how do you pull that off? Well, the solution in the 20th century, starting with Bar-Hillel actually, and also Chomsky, was that language has three main points, and then the rest of the talk is going to be replacing each of these with something else. First, that language processes arbitrary symbols, unrelated to the thing they're talking about, and it processes them using syntactic rules that don't have anything to do with the meaning of those words. Second, the language structure is dyadic, function argument, like in mathematics. So there is a subject and a complement in the sentence. And the complement has a verb and an object. So each of these is two parts, and it goes on in steadily more detail. And third, that the language processing is determined completely by the words that are sitting on the page. And I'm going to argue that none of these is true. And once you see through it, then it becomes simple and regular. And in fact, before the 20th century, there was a history that meaning did matter. There was a history that language structure had made of 3 parts, not 2 parts. And those went by the wayside with Chomsky. And there are a lot of clever things that come about from transformational grammar, but I think the active effort in linguistics to suppress any other thinking has led to the problem that you've got. So, first point, I'd say that language symbols are grounded, not arbitrary. Grounded meaning that the symbol itself has some physical resemblance to the thing that it's talking about or that it's representing. But I'll get to that part in a minute. So an arbitrary symbol, so we have a sentence here, and the standard view, but here's the arbitrary symbol cats, and it points to a thing out in the real world, cats. And my points to me, and the dog points to the dog, and there's something that we're pointing to with the word chases, okay? So that's thing out in the real world, it's the referent. So there are a number of attractions to this way of looking at things. So symbolic computations require a few things. So they require variables. So the word dog can stand for any number of dogs. It can get instantiated by different dogs. It's a directional structure rather than just being an aggregate of stuff or clustering. There's some hierarchies, you know, like my dog is a unit that's a subunit of this whole thing. And these symbols remain particular. It's not like red and white giving pink. The dog stays the dog and the cat stays the cat, which is a non-trivial property of language. And the thing that Chomsky introduced is basically the idea that you want somewhere, somehow, that the dog's chasing the cat. So somehow cats has to get here. Oh, can you guys see my pointer? Does that work? Okay, good, thanks. Yep. And so Chomsky drew attention to that problem and solved that problem. And actually, much of what I'm going to say will wind up deriving a lot of the early transformational grammar, but from a cognitive basis rather than a linguistic basis, and with a whole lot less ad hoc stuff. Now, there's a problem, though, which is, well, actually, let me point out the problem. There's nothing in these words that says how to assemble this picture. So you've got these reference, but how do you assemble it? It gets a little better if you are willing to agree that we have in our heads internal representations, which are these little thought balloons here, and that, which, by the way, is also something that people argue. You know, there's a whole school of thought says, oh, no, we don't have internal representations. But still, there's nothing here that says how to assemble these internal representations either. So what happens if we take seriously the grounding, that each one of these symbols is grounded somehow in something in the real world, in other words, physically represents it, whatever it is that's in our head that represents a dog, then you're in a little better shape. Oh, well, this is what I was saying, is that if you don't assemble them, you just get this cluster of images. Oh, and this word ambiguity is significant. So a 12-word sentence, people have shown that it can have between 10 to the 5th and 10 to the 28th potential parsers. There's only 10 to the 60th atoms in the universe last time I saw a number. So that's a problem that's generally not addressed in linguistics. And you know, in the 70s, 80s, 90s, places like IBM were trying to write programs that would use Chomsky linguistics to process language, and they failed. And the famous joke is that one of the managers at IBM said that every time he fires a linguist, the recognition rate goes up. And so while he's definitely on to something, it's not the solution to the problem. And certainly no hint as to what's going on biologically. Now, if you take seriously the grounded symbols, then you're doing computations on these representations. And that allows you to do two things that Harnad pointed out a long time ago are critical for cognition. You have to be able to compare two representations and distinguish between them. Or you compare them and look for similarities. That lets you do discrimination on the one hand, it lets you do categorization and generalization on the other. So that you have this idea of dog independent of any particular dog. Without that, you can't do cognition. And there's nothing about the word cats down here that I can compute with the word dog that's going to let me tell you whether they have the same number of ears. Can't be done. The information's not there. But it is up here if you have grounded symbols. So these are sometimes called icons. The classic one would be, say, a pedestrian crossing sign. It looks a little bit like a pedestrian crossing the street. Okay. So there's some correspondence, and now you can do computations on them. So, there is a problem, which is that we still, remember, we still want to not just point to these individual representations. We want to assemble them into higher things. So you want to assemble these two into my dog, and you want to assemble the whole thing into something about cats and dogs chasing. And you also have to get cats over here somehow. So you've got to do a computation. But if the representations are grounded, there's no guarantee that your computations on them are still going to be grounded and therefore give you a valid result. So I would say the first thing I'm going to add is that, okay, whatever the language rules are, they also have to be grounded. And so that groundedness is preserved when you're doing computations on the individual grounded symbols. So the solution to that, I would say, got two parts. One's the grounded rule hypothesis. The speaker and the listener have operations on the arbitrary symbols of words that are grounded in the external world so that they're manipulating those words in the same way that the representations would be manipulated. Or if you prefer, they actually are manipulating the representations, which is the more radical proposal, but that's, and I think that's what's going on, but I'm not going to demand that just yet. So then you can see how you could ground an object like a dog by pointing to it. How do you ground a rule? So then my second addition is what I would call the exotopic rule. So biology, the tissue, mimics stuff in the outside world. So I think you guys probably know that the arrangement of pitches of notes or sound frequencies in the cochlea is in order of the frequency. And the representation in your brain spatially is in that same order. And you have the same sort of thing for the representation of your hand and your arm. And so those are called like tonotopic and somatotopic and so forth. And you can see the same thing in genetics. You guys will appreciate this, that the homeobox genes are expressed, last time I checked, in the same order that they are arranged in the chromosome. And so biology has this habit of mimicking in the biology whatever is going outside. And so what I'm going to propose is, first of all, the way we see the world is there are things out there, there are relations in between them. And so you have two entities and a relation between them. And so I'm going to propose, first of all, that that's the structure of the world, at least as the way people see it. We don't see it as Hamiltonians. And second, I'm going to propose that, okay, there's something in our biological tissue or in these rules for manipulating representations that mimics this entity relation entity structure. So that's the exotopic rule hypothesis. So the operands are going to be these icons, these grounded symbols, or hierarchies of them. And the operations are going to build these hierarchies using only those three things, and the result of doing it is still going to be one of those three things. So then the question is, okay, so how far can you get with this? So start doing some data. So I assembled about 1,000 different sentence fragments and sentences. Not Linguistics tends to use the Wall Street Journal because usually they were trying to sell to Wall Street people. But basically newspapers are not the way we really speak. And so I took a variety of, for example, dictionaries intended for foreign speakers tend to have example sentences in them that are real world sentences. I took some books that are written by clear writers and so forth. So let's take 3 of these. I'm going to go through it slowly. It's semi-obvious, but I'm going to go through it slowly because once you get over this slide, if you're okay with me, and if you have objections, here's the time to ask. And you'll see where I'm going through. If you get through this, then the whole rest of the talk is working through the details. So the word string, and these are all taken from these corpuses of sentences. Experts predict improvements. So the meaning of that is roughly experts predict improvements. So this capital is a standard kind of abbreviation in the field, meaning intended to mean that here's the meaning of the word. And I'm going to notate this parentheses around the entities, and then the relations don't get parentheses. So you see here we have an entity, a relation, and an entity. Now, the green grassland. Well, the is pretty much what it means is that I'm going to tell you about something I already told you about, as opposed to where I'm going to tell you something new or arbitrary. Then green is pretty much like greenness, your representation of color, whatever that is. And grassland is your representation of grassland. But what I'm also saying is that the green is a component of or a property of the grassland, okay? And so I'm going to abbreviate that with this symbol here. You could think of it as the grassland enfolding this component, this property of greenness. And this green grassland is part of the things I already told you about. So the has the component green grassland. So it's a similar symbol, but facing the other direction. There's a history to this symbol, which turns out to be wrong, but it's a nice symbol anyway, because it conveys this enfoldingness. But we don't speak these things, do we? Some in Chinese, sometimes in some situations they do, but in English they don't. So we leave this out. Now here's another one, the person who threw it. So person is, some variable for a person to be instantiated, some particular person. Who is, sort of referring to something, but again, arbitrary. Through, we have a representation of throwing. It refers to some item that I've already talked about, some known item. But what we're saying here is also that this person is a component of this activity of somebody threw something. So gets another one of these things. So again, we don't speak it though. Okay. So if you're with me so far, then this is why I ask you about the parts of the chair. We never think about these things we don't speak, just sort of all subconscious. But this is data compression, which is, if you're familiar with computers, you know about data compression. If you're a linguist, you don't know about it and you don't want to know about it, oddly, I find. And so what this is saying is that when we speak in English, we're doing data compression. Here's a few more examples, and then I'll show you, well, I guess this is data. But so he met me there. Well, we don't say at, but that's kind of what you need in order to understand the sentence. They raised prices 8%. Well, by 8%. And there's more of these. He found her asleep. Well, what he found was the condition of her having the property of being asleep. And you can go on with these. Well, indirect objects are important. He gave he gave the situation of mama owning this dress. This one linguists debate about, but there actually is a history pointed out to me by Steven Pinker, actually, that there are strong arguments that it ought to be treated this way, rather than he gave mama a function that has two arguments and so forth, which is the standard linguistics way to do it. So, and then one other thing I'll point out is that gerunds are really little miniature sentences. So cooking, well, it means that something cooks something. And you just haven't said who the subject is and you haven't said who the object is. But it's an E rel E, so that's an E. You know, I can use the word that to talk about it. So it's an entity also. I'll do one more. Why do we have the word to in infinitives? What's the point? Well, what's really going on here, Casey wants Casey to change to the situation of Casey throwing the ball. Pro is a standard linguistics thing, meaning an unspoken subject. So they're onto this idea that some things are not spoken. But my point is that this is common. You see it everywhere. Oh, the horse that raced past the barn fell. That's this classic garden path sentence, because if you just say the horse raced past the barn, you're expecting it to be a past tense verb, and you've got this picture of a horse racing past the barn, and then you throw in the verb fell, and now you're confused and you have to go reread the sentence. And what you left out was the horse that was raced past the barn. Okay, so how common is this? It's about 25% of English sentences are not spoken. So these are various sources like the Longman's Dictionary of Contemporary English for non-English speakers. The Oxford Dictionary of the English Language has a whole section on examples, which are quite nice. The Penn Tree Bank, which is a standard corpus, linguistics corpus annotated for parts of speech and so forth, has lots of sentences, and there are various other things. And pretty consistently, it's about 25% of the things that are not spoken. Most of them are these system component relations, but sometimes the adverbs and so forth. Now, once we've agreed to that, so no objections so far? Great. So is there a pattern to this? Well, so now the entities are in green, the relations are in violet, and it looks like continuously you're alternating entity relation, blah, 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 blah. Well, okay, that's nice. So things are beginning to look a little less complex than language is supposed to be. Now, you can guide this or force this structure if you say that there's something like a reading frame. So you guys know genetics, linguists don't, so you'll get it immediately. So like a reading frame in genetics, you've got this pattern just waiting for the words to be dropped in. So entity relation, et cetera, et cetera, et cetera. So if we take this sentence like he saw the saw that I saw, or, so we're going to drop the entity into this box. Well, then the next box over is expecting a relation. So it's going to take the verb sense of saw. Then the next box is expecting an entity. So the goes in there just fine. Part of the dictionary definition of the is going to be that it's talking about something that's a component, something that you've already talked about. So this composed of comes along from the dictionary. So now you're in this box. So you get saw again, but now it's expecting an entity. And so this helps tremendously with the disambiguation of words, and is a clue as to why we can get away with ambiguous words. I'll show you some actual data on this point later. You can keep on going. He saw the saw, Clive saw. Well, Clive, so you're here. But Clive is a proper noun, so it's got to go here. Well, so now you got an empty space. So now that's telling you that, okay, time to do some data decompression. And we've got a table, which is not all that complicated, where you look up in the table, what to insert here, given that you've got an entity here and an entity here. And it just depends on things like whether these are proper nouns, whether it's a countable noun. They're basically, it's a table, it's a lookup table, you fill it in. If you had lots of computing time, I'm sure one could optimize that table. But I'll show you later how well this works. And so then now you're here, and then now you've got a verb again. And then you get to the period, which is basically a relation between sentences. Okay, you got another empty space. Okay, well, so you've left an empty space here. Well, actually, that's good because you really want this saw over here to wind up over here, just like in transformational grammar, because Clive saw that saw. And so I'll talk later about how to do that. But you can see that this sequencing template simplifies everything. Now, I want to make 2 points. So it simplifies the disambiguation and data compression. But if the word is ambiguous, the dictionary alone and the word alone can't help you with it. It can't tell you where to place the word in this series of boxes. Excuse me. So this template has to be exogenous to the sentence. It's not contained in the words on the page. And I think there's no other place for it to be than up here. And I think this is the thing that humans have that lets us process language. There's actually a whole literature in linguistics arguing that some of this structure comes from a previous ability to synchronize muscles in order to throw things. And I think that's probably on the right track. You already had some kind of sequencing track, and now you've learned to put words into it. The other thing is that if you're inserting gaps like this, well, that also can't be part of the words on the page. It has to come from an exogenous sequencing track. And for those of you who are, like Dr. Priston, who think about Bayesian sentence processing, I would say that, okay, here's the backbone. Yes, you can add sophistication onto it. And I'll show you later how much sophistication how much you get from this alone and how much additional sophistication you need. Okay. Now, so far we just got a string of Israels, entities, relations, entities. Now we got to build them up. So now I'll tell you how to do that. So this is the next thing. So we're on number 4. The first 3 are me saying that the 3 things linguists are doing in the 20th century are wrong. And now the next set of things are going to be things we can do now that they can't. So how do you build this stuff? Well, so here's another sentence just from the corpus. Saracens built a network of highways to serve blah, 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 blah. So Saracens built a network. So this all goes as I've been telling you. Now you get to of. What you want to happen is a network to be an entity now. And so we'll say for the moment that someplace around the word of, there's an operator that's building things. And what it's going to do, it's going to build a network. Now, it could do it again and Saracens build a network of. And if the next word were bricks, that would probably be the right thing to do because you'd have of as an adverb. But in this case, it's not the right thing to do. So you've got a preposition here, and you're just going to build this. This is all called prepositional attachment, and it's largely an unsolved problem in linguistics. And for us, what we do in the computer program I'll show you later is we do it both ways. And what will happen if you guess wrong, sooner or later that parse dies because there'll be some other conflict that it creates. Now we keep on going of highways. You get to 2, and now if we take the adverbial sense, you would say, okay, now the adverb is going to build this whole thing, and then it does get to do it again. So you built a network of highways, and now it does it again. And you get Saracens build a network of highways. Why? Well, to serve the practical needs of commerce, and you do more parsing. Now, if it had been, they built a network of highways to nowhere, this would be a preposition. You would build highways to nowhere. Well, to wouldn't, down here would someplace. And so you would not be doing this. So that's another fork that you could take. But in the present situation, it's this one. Okay, great. So actually, all these operators are sitting right at the same place as the relations. What are the rules for these building operators? Well, turns out that the building operators are the relations. They're not just sitting there, they are the relations. And we sat down to figure out what those relations, what those rules are, because we figured, okay, this is going to be complicated. You know, in such and such a circumstance, it can only build this far. In other circumstances, it can build twice in a row. Or maybe it only builds from here to here and somebody else builds from there. Turns out it wasn't complicated. So those of you who are engineers or computer guys, or even if you remember algebra, operator precedence hierarchies, you know, you multiply first and then you do addition and subtraction. Or you do the exponents first, or then you do the multiplying and dividing, and then you do the addition and subtraction. So for a given operator, it's somewhere in this precedence hierarchy. So you can just, turns out, I was amazed, that you can just write an operator precedence hierarchy. So that's just another table. And you can sort of see things like this guy who comes after the are pretty low down. You almost always build over him into something bigger. Whereas things like periods and question marks, you almost don't, well, you don't. And then other guys are in between. So then the next thing I'll show you is these Chomskyan, let's see, I wonder what did I do? I had a clock. I don't know where I put it. So the transformations, actually, oh, I did what I never do. I put it in my pocket because I thought that would be a good idea. Okay, now, so can you do the Chomskyan transformations? Well, they have a series of rules for how to get cats into here. They're pretty good rules, but they're a little bit ad hoc sometimes. But here, there's this next amazing thing. On the basis of two words flanking an empty space when we did the decompression, remember we inserted these various relations? Well, it turns out that for some reason that I really don't understand, these same relationships also act at a higher level. So we can now say, cats, oh, okay, we said that they are a component of this whole thing. Well, they are a component of that. So cats go into that. Well, that is a component of this whole thing. And guess what? There's even empty space for it. And so that's called successive, what is it? I forget what it is. Anyway, in standard linguistics, the point is you do have to do these things in steps. And here, all the algebraic instructions have already been inserted for you. So poof, all you have to do is the computation. And similar things, well, I won't go into that. Similar rules can assign, well, actually, I may have mentioned it. Yeah, so where you start and where you end are governed by some rules. And it's called C command in linguistics. There's a complete analog here. You just have to rewrite it in terms of entities and relations. And same kinds of rules for deciding on the relationship between pronouns and reference. If you violate those rules, the sentence isn't grammatical. So that's how you tell a grammatical sentence from an ungrammatical sentence. Now, this is only English. So here's Lakota, which is the Sioux language. So where we would say, John found that letter under the bed, in Sioux, it is John letter that bed the under found. Okay. That can be written as rel. There's a phenomenon in linguistics where you can classify languages according to different structures. And this, EREL-E happens to be one set of languages, EEREL is another. And this is essentially like reverse Polish and, in mathematics or computer programming. But you can do it, and it's the same general idea. So let me show you a little bit of what happens with actual parsing of this. So Steve Senf, who was at Yale at the time, he's now at Marine Biological Laboratory in Woods Hole. He's the guy who wrote the original voxel view program that processes images, three-dimensional images in terms of voxels instead of pixels. So he wrote a program that's only 8 megabytes. Half of that is the dictionary, so it's only 4 megabytes of processor, as opposed to these large language models, which are terabytes of RAM. So here's just an example that's sort of a hard one, and you probably have to read it twice. The man who Aaron knew Clive called. And there's actually 2 meanings that you can take out of that. The man who Aaron knew already, that person knew Clive called. Or the man who Aaron knew that person knew Clive called. And this program spits that out. It also is able to pull out of this who did what to who. So in this first one, the man knew something. Clive called somebody, and Aaron knew the man. Whereas this one is different. The man called somebody, Aaron knew something, and the man knew Clive. And you may be familiar with pretty print, which is supposed to be a way of showing hierarchical structure. Steve came up with this other notation, which I think is much clearer. If you just look at this, you can say, well, okay, somebody knew something. Well, what did that person know? He knew that Clive called somebody. Well, over here, who knew something? Well, these guys are all just variations on those left and right component of symbol. So the man, if you look down at this level, the man is a component of something. It's a component of who Aaron knew. Who is a component of Aaron knew, because Aaron knew this guy who. And the man is a component of all that, and it's a component of the who, etc. So it's all built in there. I can, run a program in real time for you if you want. It's probably simplest just to finish the talk, and we could play with that later if you want to run any sentences. So, and there's also a cost function. That's what this is. So that if you have to start skipping boxes, you can do it, but it costs you. And so that's a way of telling whether you're doing something that's legal but unlikely, and sooner or later, those things wind up having a huge cost, and that's not right. Now, does it work? So I'm guessing you guys don't worry about linguistics much, but there's some standard metrics, like recall and precision for this thing are 97%, coverage and consistency are 77%. Basically, consistency is how many correct parses do you get? Well, let me just say that when people do this, they use things like the Penn tree bank corpus, which doesn't even bother with compound nominals like doghouse or prepositional attachments, like I was showing you the two different ways of doing of. It doesn't even annotate for that. I've annotated for that, and it's still 77%. If I didn't annotate for that, it's probably 97%. And then there's cross brackets, which has to do with, well, how many subunits is the computer trying to get you to say overlap each other when they shouldn't? And it's rather small, and it only happens in really long sentences where people get confused. So, to show you some data. So I told you there are lots of, because of word ambiguity and the resulting parse ambiguity, because parsers build things differently than entities, there's a lot of alternative parses. So on the x-axis, you have the number of words. So let's take a 15-word sentence. And so the sentences I tried, they have about 10 to the 7th possible parses. Oh, I forgot to show you. Back here, it's saying that for the man who Aaron knew Clive called, it's saying that there are 3,800 potential parses, and it's pulled out two. Both of them are, correct. So back here, so you've got 10 to the 7th potential parses, and you've dropped that down to about 50, let's see, 10 to the, so one, yeah, so this is, it dropped it down to about 10 parses here. So that's pretty impressive. So what you're doing is removing, with just this sequencing track and these cognitive rules, you're removing orders of magnitude of the ambiguity in the words and the alternative ways of parsing a sentence and understanding a sentence. And so now you're only down to here. And so that any knowledge you have to have about, well, what's the guy probably trying to say, or any of the Bayesian stuff, only has to solve another like tenfold of this. This ratio here turns out to be a reduction of 2.74-fold per word. So threefold. But that 3, if you start raising it to the 15th power, gets to be a big number. Then as I stared at that, I was thinking, oh, 2.74, that number looks kind of familiar. And then I realized that this reduction here is 1 over e to the 1.008. In other words, it's 1 over e. And so the interpretation of that, there's a kind of like a target theory interpretation of that in statistics. If you're trying to hit a target with radiation or something. Basically, there are enough constraints that in the cognitive rules I told you about, that you are just going to stochastically eliminate sentences that are wrong. And so you're reducing things down to 1 over e. And then what's left, and that is what happens when you have independent events. So it's treating words as more or less independent. And the collisions are coming from the sequencing track rules. Then everything else you need to get from this 10 down to a single interpretation is either the meaning or things like subject-verb case agreement, or subject-verb number agreement, or cases, things like that that are relationships between a couple of words. They're not independent events. And so that's what the rest of linguistics is doing, is getting you from here down to here. Now, I hope at this point I've convinced you that, gee, language is maybe a whole lot more regular than we thought, and having a regular algorithm can process way more of it than we thought. And you could then wonder, oh, and that what it's processing is building are these representations rather than words per se. And then now you begin, so let's wonder about AI. So what have large language models discovered? All they would have to do is discover or teach themselves to make a sequencing track like this in a couple of rules. And a sequencing track, what is that? It's just a series of probabilities. Oh, well, if I am an entity word now, the probability is 1.0 that the next word is going to be a relation, and the probability of that is blah blah. So it's sort of Bayesian, but it's um, as somebody told me, well, rules are just probabilities of 1.0. And so a statistical learning machine could come up with this track. And then what are the implications of that? Well, let me show you one more thing about how this program works. So we're trying to build a sentence, build the parts into higher and higher hierarchies. So what we're doing, I'm going to show you that basically we have a shift register for grounded symbols. So you have cats, that, because the dictionary definition of that is it has these two component things, because cat is going to go into that, and that is going to go into something else. Cats, that, my dogs, blah, 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 blah. You keep building here. Now chase is a relation. These guys don't build much. Chases will build things. And what you want it to do is build my dog. Well, what it does is it does the shift register thing. It's going to put the composed of and dog all in the same box, because that grouping is now an entity. And it shifts these guys over too. And then keeps going. It gets to R. And then R is going to build. And now it's going to shift the parentheses and chases all into this box and put a new set of parentheses around it. Oh, these things are all just parentheses. They're just different shaped parentheses to make it easy to follow. And then we're going to keep on going, because R goes all the way to the beginning of the sentence. It's going to shift it over again, lump all these things together, shift over again, lump these things all together. And then all you need biologically is, instead of parentheses, you need something that is going to group these subgroups into a bigger group without just averaging them like red and white into pink. Well, if then you think about whether representations could be doing this, whether your brain could be doing this on representations in addition to just doing it on words. These words are really just representations too. There are no words in your head. There's just like neural spikes, right? So these guys, so you've already got representations getting dropped in here. What happens? So it doesn't seem to me a very big step to be dropping these representations into the same sequencing track and doing the processing. So if a large language model happened to invent the sequencing track, it could also support processing of sensory representations instead of word representations. And I've just shown you that the rules are the same. And then if that then lets it assemble complex representations, and it does so in a way that you can now define a thing, which is the one remaining part, which I have an idea about how it could do it. Because what we think about are things, right? But it can now, it retains all the information to do discrimination between them and do generalizations. So that fulfills Harnad's definition of what it takes to do cognition. And so I'm quite concerned that these large language models are accidentally going to stumble across a way to be doing cognition. So that is, I believe, it. Yep. And open to any questions, or if you want to see the parser in action, that's fine too. And I will